students, from today we are going to start complex numbers. Our first chapter is complex numbers. First of all, see what is complex number. Complex numbers can be defined as ordered pairs x, y of real numbers that are to be interpreted as points in the complex plane. With rectangular coordinates x and y just as real numbers x are thought of as points on the real line. Means what? Complex number can be defined as ordered pairs x and y of real numbers that are to be interpreted as points in the complex plane with rectangular coordinates x and y, and these x are thought of as points on the real line. When real numbers x are displayed as points order pair x0 on the real axis, it is clear that the set of complex numbers includes the real numbers as a subset. Means what? Set of real number is the subset of set of complex number. Okay. Complex number of the form order pair 0y corresponds to the points on the y-axis, and called pure imaginary numbers. numbers when y is not equals to 0. Order pair 0i correspond to the points on the y-axis and called pure imaginary. This number is pure imaginary number when y is not equals to 0. The y-axis referred to as the referred to as the imaginary axis. Okay, means what? Complex number, it is denoted by order pair xy. This point x0 is corresponds to the points on the real axis, and this order pair 0y corresponds to the points on the y-axis, and this is pure imaginary numbers when y is not equals to 0. In next line, write down complex number order pair xy denoted by z such that z is equals to order pair xy. The real number x and y, this x and y are real numbers. X and y are known as real and imaginary parts of z respectively. Real and imaginary parts of z respectively. We write x is equals to real z, means x is real part of z and y is imaginary part of z. In next line, again write down two complex numbers z1 and z2 are equal whenever they have the same real parts and same imaginary parts same real part and same imaginary part. That is the statement. Therefore, the statement z1 is equals to z2 means that z1 and z2 corresponds to the same point in the complex, or we can say that z plane. Two complex numbers z1 and z2 are equal if and only they have same real parts and same imaginary parts. Okay, the statement z1 is equals to z2 means what? z1 and z2 corresponds to the same point in the complex or z plane. Okay, the sum the sum z1 plus z2 and product z1 into z2 of two complex numbers is defined as follows. Okay. Order pair x1 defined as follows. Here z1 is order pair x1 y1 and z2 is order pair x2 comma y2. So z1 plus z2 is nothing but order pair x1 y1 plus order pair x2 y2, which is nothing but x1 plus x2. Here take component wise addition. y1 plus y2. Okay, this is sum of two complex numbers. Now see what is product of two complex numbers. z1 into z2 is equals to order pair x1 y1 into order pair x2 y2. This is nothing but x1 into x2 minus y1 into y2 comma y1 x2 plus x1 into y2. Okay, I will explain this product in next topic. Let us first write down note. First is operation. Suppose call this equation 1 and call this equation 2. Operations defined by equations defined by equations 1 and 2, operation defined by the equation 1 and 2 become the usual operation, of addition and multiplication when restricted to the real numbers. That is, imaginary part is 0 plus x2 0 is equals to, suppose this is complex number z1 and this is z2, in which imaginary part is 0. At that time addition and multiplication become usual operations. That is x1 plus x2 0, x1 into 0, x2 0. This will also x1 into x2 coordinate wise multiplication 0, because this complex number is restricted to the real number. Okay. second, the complex number system is a natural extension of the real number system of the real number system the natural extension of the real number system. Okay. Third, any complex number z is equals to order pair xy can be written as z is equals to order pair x comma 0 plus 0 comma 1. Means if you take addition of these two numbers, we will get z is equals to xy. And it is easy to see that, order pair 0 1 into 0 y is equals to order pair 0 y. Therefore, z is nothing but order pair x0 plus order pair 0 1 order pair 0 y. Put here order pair 0 1 into order pair 0 1. Suppose this is equation star. If we think of real numbers as either x or order pair x0, if we think of real numbers as either x or order pair x0, and I denote the pure imaginary number. I denote the pure imaginary number, pure imaginary number 0 1. So equation star becomes z is equals to x plus I y. So students, keep in mind that any complex number can be represented as order pair xy or z is equals to x plus I y. Okay. So in next line write down, because order pair xy is nothing but x plus I y. We have just seen it. Therefore, definition 1 and 2. Definition 1 and 2. Definition 1 and 2 means what? This is product, and 1 is what? Z1 plus Z2 means addition of two complex number is what? x1 plus x2 comma y1 plus y2. This is our 1. Okay. Now here order pair x1 y1 means what? x1 plus I y1 plus x2 plus iy2 is nothing but add imaginary part, sorry, real part and add real part, imaginary part. So we will get x1 plus x2 plus I into y1 plus y2. Okay. Now take product. x1 plus I y1 plus x2 plus I y2. Okay. So x1 into x2 real part is I into I is, students, again keep in mind that I square is minus 1 or I is equals to root of minus 1. Okay. So here x1 into x2 minus I square is minus 1. y1 into y2 plus I into x1 into y2 plus y1 into x2 plus y1 into x2. Okay. Next is any complex number times 0 is 0. Okay. That is z into 0 is equals to x plus iy into 0, which is equals to 0 plus I0, which is equals to 0. This is for any z. For any z is equals to x plus iy. Okay. Now see basic algebraic properties of complex numbers. Up to we have seen sum and product of complex numbers. Now see basic algebraic properties. Basic algebraic properties. First property, sorry, before that write down, let z1 comma z2 z3 be any three complex numbers. Any three complex numbers. Then first property is z1 plus z2 is equals to z2 plus z1. This is commutative law. You know, all of you very well. This is commutative law. This commutative law with respect to addition and with respect to multiplication is z1 into z2, z2 into z1. Second one is z1 plus z2 plus z3 is equals to z1 plus z2 plus z3. This is a associative law, and with respect to multiplication is z1 into z2 z3 is equals to z1 into z2 z3. This is associative laws. Okay. In this also write down z1 into z1, sorry, z2 plus z3 is equals to z1 into z2 plus z1 into z3, z1 into z2 plus z1 into z3. Distributive law. Okay. Third is z plus 0 is equals to z. Here 0 is equals to order pair 0 0. This is additive identity. identity. Additive identity. 0 is additive identity, and z plus 0 is equals to z for any complex number z. Okay, you write down for any complex number z. Okay, this is third. Fourth is z into 1 is equals to z. Okay. 1 is equals to order pair 1 0. Obviously this is multiplicative identity. Multiplicative identity. Multiplicative identity for any complex number. Okay. Fifth, for all z, which is x plus iy, or we can write order pair xy. So here just write down order pair xy. There exist additive inverse. There exist additive inverse minus z is equals to my order pair minus x minus y, such that z plus minus z is equals to 0. There is only one additive inverse for any given z. Students, always remember that there is only one additive inverse for any given z. Okay, therefore the equation xy uv is equals to, suppose this order pair uv is a additive inverse of this complex number, then what we will get? X is equals to, u is equals to minus x and v is equals to minus y. Means additive inverse of order pair xy is order pair minus x comma minus y. Okay. Fifth, for any non-zero complex number, for any non-zero complex number, for any non-zero complex number, z is equals to order pair xy. There is a number z. There is a number z such that z into z inverse is equals to 1. Here z inverse is multiplicative inverse. Z inverse is multiplicative inverse. Okay. We will find multiplicative inverse. We will find multiplicative inverse. We will find multiplicative inverse of z by using, suppose order pair z is order pair xy and its inverse is uv, which is equals to 1. Students, this is homework to you. Find the values of u and v. That values or here I will write down multiplicative inverse of z is equals to order pair xy is z inverse is equals to x upon x square plus y square minus y upon x square plus y square. This is homework to you. Find out this z inverse. Okay. Write down z inverse is not defined when z is not equals to 0. If z is equals to 0, then z inverse is not defined. Sorry, here z inverse is not defined when z is equals to 0. Okay. Let us take example. Example is, first example, verify that a root of 2 minus I into 1 minus root of 2 into I is equals to minus 2I. We have to verify that. That means we have to show that LHS is equals to RHS. Here LHS is equals to root of 2 minus I into 1 minus root of 2 into I. Take multiplication of this. Sorry. This is root of 2 minus I. This minus into minus is plus. Okay. And I square is minus 1. That's why here we will get minus root of 2. Okay. Root of 2 minus root of 2 get cancelled. Here remains minus 2I, which is equals to RHS. Hence LHS is equals to RHS. Okay. Now take for homework order pair 2 comma minus 3 into order pair minus 2 comma 1 is equals to order pair 1 minus 1 comma 8. C. Order pair 3 comma 1 order pair 3 comma minus 1 into order pair 1 comma 5 comma 1 upon 10 is equals to order pair 2 comma 1. Okay. Okay students, so we will stop here. Thank you.